So I've pulled out some technology examples here to show you how different technology would report that regression line. So I'm a big user of the programming language R, that's what I make all my slides in, and this is how it would tell me about the regression line. It would say the intercept is 99.62 and the slope is 4.8. Jump maybe gives me more decimal points when it reports it. Minitab, we've got this column with the coefficients, but then it also has the regression equation written out for us. SPSS has the coefficients here, so they're all finding the same number. It's not that different technology is going to find different numbers, they just report the information differently. And you'll learn how to fit a linear regression in your lab in whatever software it is that you use. So at the beginning, I said that we put the explanatory variable on the x-axis. So this should be the explanatory. And we put the response on the y-axis. And unlike with correlation, in regression, it does matter which variable is the explanatory and which is the response. So this is the equation when I use volume as my response and average temperature as my explanatory. But if I flipped my variables and I was trying to predict the average temperature based on the volume, I would get a totally different equation of the line. And so it's important to think about which one is your explanatory and which one is your response. I think that's an easy mistake to make. So there are a number of things that we can do with our linear regression model. We've seen how we could use it to make predictions or to calculate residuals. I think one of the most important things to do is to be able to interpret the values out of your regression equation. So remember, we've got our estimated regression line, y hat is equal to a plus bx. The slope is b, and that's the increase in the predicted y for every 1 unit increase in x. And then the intercept, that's a, that's the predicted value when x is equal to 0. So if we plugged in 0 here, then this part of the equation would go away and we'd just have y hat is equal to a. So let's think about interpreting the slope and intercept from my model. So the slope is the 4.8 value. It's the thing that gets multiplied by my x. And here's my favorite way to write the sentence. For a 1 degree increase in temperature, we would expect approximately a 5% increase in the number of riders. I think the textbook has a slightly different favorite sentence, which would be the predicted number of riders goes up by about 5 for every increase of 1 degree in the average temperature. And either way, you could use either of these as kind of your recipe for interpreting the slope. You don't have to get creative when you interpret the slope. And so I will write out the kind of generic sentence that I'm using as a recipe for my sentence here. So my generic sentence is for a 1 unit increase in x, we would expect a b unit increase or decrease in y. And so if we look at this sentence, the pieces that you would need to change are the units for your x. You would need to plug in x. You would need to plug in b. You'd need to plug in the units for b. You need to decide if it's an increase or decrease, and you need to plug in y. So in this case, I know that x, the units of x are degrees. So for a 1 degree increase in average temperature, we would expect a 4.8, or you could round to 5, 5 person, because that's the units for y. And then I know it's an increase because this is a positive slope. If it was a negative slope, I'd say decrease. So a 5-person increase in the volume, the number of riders. So it is always a 1 unit increase and then a b unit increase or decrease in y. So you can just use that, that recipe. For the intercept, like I said, what we would think about here is plugging in 0 for our x. So if we plugged in 0 degrees, then this term would disappear and our equation would just be this. And so the intercept is that 99.6. So if the temperature were 0 degrees, we would expect about 100 riders on the rail trail. And both of those interpretations tell you something about the relationship between average temperature and volume. So these can be really good sentences to include in like a report. Just like with correlation, we have some cautions about regression. So one is it's important not to make predictions outside the X range of your original data. So if you predict outside the range, it's called extrapolating, and extrapolating is bad practice. So if I was thinking about my example with the rail trail, it would be okay for me to try to make a prediction at 40 degrees, even though there wasn't any day that was exactly 40 degrees, but that's in the range, or 50, 55, 60. But if I said, okay, what if it was, okay, so this is 80 degrees. So I think that 90 would be here and 100 degrees would be here. What if I said, what would the predicted value be for 100 degrees? That is a bad thing. This would be extrapolating, because the hottest day that we had in our data set was like 85 degrees maybe. So I can't make a prediction for 100 degrees. And what that means on the other end is if none of your X values are near 0, you shouldn't interpret the intercept. And so that is probably true here, that I had 30 degrees, and if we went back, there'd be 20, 10, 0. I probably shouldn't interpret the intercept because it's so far outside the range. Another thing is that computers will find the regression line for you, even if your variables are not associated or the association is nonlinear. So just like with correlation, it's very important to always plot your data. If we had the datasaurus data and we had just said, R or Minitab or SPSS, find a regression line for us, it would have found this slightly negative regression line. But that is not an appropriate way to summarize this data set. It does not look linear at all. And then you should only use linear regression if the association between the variables looks roughly linear. So if you had something that looked like a nonlinear relationship, so this is a relationship between the displacement, like the sort of size of an engine, and the mileage that car gets, and it looks a little bit less than linear. So I think that the better fit for this data set would be kind of a curve. And so we should not be fitting a line, a straight line, because that is not a good fit for the data. So if you see data where it seems like a curved line would fit better than a straight one, you should not be using linear regression. Another caution is that outliers can have a big influence on the regression line, and so you need to make sure that you plot your data. So in this one, I just took the datasaurus data and I added in an outlier way outside in the plot, and that made my regression line way steeper. So it dragged the line up. I think before the line was, pretty flat, but then once I stuck in one outlier, then the line got dragged way up. And it turns out that if you have one outlier and it's way outside the data, you can basically make the regression line be whatever you want. So if I had wanted to make this regression line be negative, I could have put an outlier way outside the range of the data and really negative. So again, you want to plot your data so that you know that linear regression is appropriate. And then finally, higher values of X might be associated with higher or lower values of Y, but that does not mean that changing X causes Y to increase. The only way that we can determine causation is if we have an experiment and the values of the explanatory variable were set at random. That's super rare. So you should not be making causal statements. So even with my example about the rail trail, I can't say that warmer temperatures cause more people to go outside. There could be something else going on. There's probably, a relationship also with the day of the week and holidays and things like that. And remember, we've got our spurious correlations. Even if we had a nice equation where we could predict how much uranium was stored at a US nuclear power plant based on the number of math doctorates, it's not that if we increase the number of math doctorates, we'd expect to see more or less uranium at the power plants. It's not a causal relationship. So the big takeaway from everything with two quantitative variables is always plot your data.